Okay, so in the previous video, we established that this E test is an estimate for E out of G, and we looked at how that is possible in an ideal world scenario, right? And so we have access to all the data that we want, and then we found out that there is this expectation of E test, which is like E out, and then the variance is given by 1 over k variance of the error for every point. And as you can see, this decreases in a 1 over k. Okay, so the question that we asked was, can we do something in a real world because we don't have access to all the data? And so to answer that question, short answer to that question is yes, we can do that using something that's known as validation. So we are going to look at what this validation is all about. Okay, so now going back to our original, so we'll have some limited data, and let's say it has like n data points. I'm denoting it by d of n, right? And we want to get, like for validation, we want to get E of out, right? E out, essentially. So how do we do that? Because I don't have like anything apart from this dn, which is like my sample. So the way to do that is that I'm going to randomly split it into two parts. So I'm going to randomly split this d of n into two parts. And how do I do that? Let's say I pick randomly any k points, independent test points, and I'm going to create a data set called dk because this has like these points x1, x2, let's assume up to xk, right? And so the rest of the points will remain here, and those are so I'm denoting them dn minus k. So basically they'll have like starting from k up to n, all the points here in this data set. So we have split it into two parts, and I've done a random split. And in the terminology of validation, this is known as the validation set, and we'll see why. So this is the validation set, and this is my training set. So why is this the training set? That's because I'm going to train my algorithm using this data, this dn of k, n minus k. And so I'm going to get my final hypothesis G using this n minus k. And of course, this is like different than the G that we've been using until now, because we've been assuming that that G is based off of like the entire data set, which is not the case here. And so I'm going to denote this hypothesis by G negative. So this negative is essentially denoting the fact that this hypothesis is deficient due to fewer data points. So this is like a deficient hypothesis because I have used fewer data points than I actually had, right? Okay, so once I have this G negative, similar to the process that we adopted last time here, what we did was, like based on these n data points, I picked up the final G, and based on that G, because this error is a function of G for each of these points, test points rather, I calculated this error, and then the average of the error was my test error, right? So we are going to like follow a similar approach, except that we don't have access to all the data. In fact, we are trying to simulate that real world, but with a deficient hypothesis, and hence a deficient data set rather. So in order to do that, I'm going to again calculate these E's that we calculated in the previous one, which is E1 calculated on this deficient hypothesis, which is G negative, and then E2 on G negative, and so on EK, G negative. And so the estimate, now we are after the estimate of E out in validation, as I said when we were starting with the lecture, right? Now, we are going to calculate the average of these errors just like we did in the case of the test set. But now this estimate will be known as the validation error, because now we call this a validation set. Why? Because this is part of my original data set itself. Okay, so what I'm going to do is I'm going to average for all k points. K is from 1 to k, ek calculated on this deficient hypothesis, right? Okay, so as I said, this is known as the validation error. The rest of the discussion holds, just like here, whatever we got for the expectation for E test, which turned out to be E out, and then the variance of E test, which was 1 over k, variance of each of the error for each of the points. So similar to that, all that discussion holds here as well, because just like the original data, we have this data that's generated randomly, and then also the expected value that we'll calculate will be with respect to the generated data, right? So essentially what I'm trying to say is that the expectation of eval, just like the expectation of test, was my out, with the exception that this is going to be G negative. Why? Because the E out that I'm going to output using this hypothesis is going to be a result of the deficient hypothesis, because I have separated or split this data into two parts, right? And so similar to that, the variance of this eval, or the variance of this error, is again going to be 1 over k variance the error that's calculated over the deficient hypotheses. Again, like the entire analysis still holds, with the exception that my hypothesis is a deficient one. Okay, all right. So let me summarize it just the way we did there. So this is the validation set. Now we are trying to simulate the real world analysis that we did. And so we did this have n data points, split it into two parts, n minus k and k, and then calculated the average error, which is the estimate for my E out. But notice this G negative because that's the deficient hypothesis. And because these are independent points, again, the same analysis holds and we have the variance. Now you can see that the variance decreases with as I increase k, right? So eval is, you can say, if we look at this, here, right? If we just look at the eval value, as I increase the size of k, which means when I'm saying I increase the size of k, I'm essentially increasing the size of my validation set, right? So as I keep more and more points into that validation set using which I test my hypotheses, right? So if I increase that, right, what happens is my eval, if I increase this, what happens? If this goes up, this goes down, right? So my eval will begin to drop, which is good, right? So basically this kind of tells me that how about I actually have k equals n, put everything in my validation set, then what happens, right? So then, well, nothing much happens. This D train will have no data, right? I'll be left with no data. And why is that bad? Because I have nothing to train on. And so most likely what will happen is that this G negative or G minus would be any random hypothesis, right? And so any random hypothesis means it has nothing to do with the data because I don't have data. So I just picked up any random hypothesis, which means that when I'm finally trying to estimate E out G minus, that is going to be this error is going to be huge. Why is it going to be huge? Because this G minus will be extremely deficient. It doesn't have anything. It's not even related to the problem that I'm trying to solve, right? So therefore, eval will go up as it is an estimate of E out, right? So this thing, so essentially what's happening here, right? We said that this is good, but actually it's not, because there is a trade-off. And even when we look at this variance term here, what's happening in the variance term? K goes up, so then variance goes down, right? But then variance is dependent on two terms, the first one is 1 over k and the other one is this variance of E that's calculated on G minus. And so it is dependent on G minus and the way we got to this G minus, right? And so when we are calculating that variance, that's going to go up because we are calculating this error on a deficient hypothesis, and an extremely deficient one rather, because I don't have any data there. All right. So having said that, let's look at this trade-off and how this comes into picture and what is a good k that we should have, because we said that this k equals n looked really ideal, but then that's not the case. So there has to be some way to address this trade-off, and that's what we're going to look. All right, so let's say we have some way of plotting this error, and let's say here is my error and here is my k, right? So this is the size of k is nothing but the size of my validation set, right? Now I know that there's this product of 1 over k times variance, this thing here, right? That is representing my variance, and then there is this E test or my expectation of my E, not really E test. Here, the expectation of my eval is essentially, basically I'm trying to estimate E out using eval. This is what these two equations are, right? Okay, so when like I'm increasing the size of this k, what happens to my eval? Because my eval is calculated on my, it's nothing but the average of all the errors that are calculated on my G negative or G minus, whatever you like to call it, right? And so when I'm increasing this k, I'm making this more and more deficient. So basically, this is like getting worse with an increase in my k, right? And so when I'm calculating this like E of G negative for like any point, this should, like ideally speaking, go up, right? So if this is the expectation of my eval, fine. Now with variance, remember there are two terms here. So one is 1 over k and the other is the variance of Eg minus. So of course, as like when we begin to increase k, this variance will go down because of that 1 over k. And so it will look something like this. It starts to go down. But then because of that second term, which is dependent on my E of G negative or G minus, right? This is going to start to go up somewhere here, right? And so this is the variance of eval, and that's the expected value of eval. And so my overall error is essentially a sum of these two. And so what will happen is it should be something like this, right? Initially, maybe it's like more flat here and not going as much down. And then eventually it starts to go up because as I'm increasing k, this is getting worse and worse. So basically the idea, the intuition here is that there is some k star here, which is my optimal choice, which should be my optimal choice, right? And so based on this idea, what's going on is that in practice, there is this rule of thumb that this k star should essentially be n over 5, or in other words, k should be like 20% of the overall data that you're using for training. So this is how we kind of come up with an optimal k, and roughly speaking it's n over 5. I would say sometimes you can do a little bit of like change, like maybe make it greater or less, but roughly this is the value, and this has been like people have come up with this from practice. Okay, so this is how we get a good k, because we don't want our hypotheses to be like extremely deficient, but then we don't want the variance to go high. So we have to have a balance. All right. So having said that, let's move on to what exactly were we trying to do, right? What was our goal in when we started talking about this validation? Okay. So the primary goal always, because like why are we showing you this thing here, is that although we are calculating this eval for this deficient hypothesis, which is like G minus, right? But the primary goal here is to output the best G. And this best G must be trained on the entire data set, which is of size n, right? Because understand that this is like this part is happening behind closed doors. We don't give it to the customer or the client. So, but this is behind closed doors, which means we have to utilize the data that we have, and we cannot just like get rid of that, right? So that's what restoring D or restoring data set means. And so that is the primary goal. And then the secondary goal is that we have to estimate E out of G. And so we found out that the good estimate of E out of G was eval, and eval was based on this deficient hypothesis, right? Okay, so how does this all of this play a role? Now we know that we have to take out some like k points for validation and then use only n minus k points, right, for training, right? But then this will cost us in terms of E out, because I'm not taking like the entire information that's provided my D into account. Like I'm just throwing away something because I just need an unbiased estimate of E out. And so the purpose of validation is to estimate the out of sample performance, and eval is a good estimate of E out of G minus, right? Well, that all of that is good, but what we need is that we don't have to output G minus as our final hypothesis. We cannot give the customer, basically what this means is we cannot give the customer G minus, because why are we getting rid of the other information that's there in like n minus k points, right? So the primary goal is to get the best hypothesis, which was this here, So we should output G, the hypothesis that's trained on the entire data set D. And then the secondary goal was to estimate E out, which is what validation allowed us to do, right? And so based on a discussion of like what we saw here, the trade-off that happens, right, we can come up with some relationship between E out of G, like this thing, and E out of G minus. So let's look at that. What exactly is the relationship? So what is this E val versus E in? Oops. And so what we're going to do is, let me write it down, E val versus E in. Let's analyze like in through the lens of VC theory. So we know that E out of G, right, according to VC theory is less than E in of G plus some term that's of the order VC dimension, right, log n over n, right? And this term here, it depends on the hypotheses set, the entire hypothesis set. Now, when we look at what we are doing now with validation is that we are calculating this E out of G minus. Let me write it down first, E out of G minus, which is a deficient hypothesis, and we are saying that this is less than or equal to E val plus some term of the order 1 over square root of K, which was the variance term essentially, right? So now this term here is based on, first of all, single hypotheses, not a hypothesis set, right? So this is also known as single hypothesis Hofting error bar, because this eval was calculated on one single hypothesis. Okay, now what is the relationship between this E out of G and E out of G minus? Well, there's this is not a theorem, but this is practical truth that this is always less than or equal to this E out of G minus. So there's this slack that exists in most practical situations, and so when if K is small, and then the slack is going to be small, right? So we have these two bounds, I can say, and we have access to both bounds, and now we have this new relationship between E out of G and E val in some way, and it's up to us which one we want to use. So this new one is based on validation error, and like you can control the second one because you get to decide like what is your K, right? And eval is known to give a better estimate of E out. So eval is a better estimate of E out of G, usually speaking. Although we have like trained it on a more deficient data set, so to say, because like we first like train it with n minus, we got rid of k points and we trained it only on n minus k points, and then we validated it with the k points. And then we can still give E out of G based on this relationship. We can still say that this like E out of G is going to have some sort of relationship with this like deficient um, like the E out calculated on the deficient hypothesis. So the idea being that we are calculating this validation error, which is in practice a very good estimate of E out, although it was calculated on a deficient hypothesis. So that's the fundamental idea. Okay, so how do we use this validation, how useful it is, and what are the applications of this? We're going to look at that in the next video.